Hello class, this is the pre-class video for 3.2. You'll be happy to know that one of the hardest things in this section we've decided not to cover this semester. We've just decided as teachers of linear algebra that it's not that important. There's more important things for you to cover. So any problems on a set of matrices that are linearly independent or linearly dependent, those kind of problems we're not going to require you to know for the exam. So this section starts us in with matrix algebra, where a lot of this will seem familiar because you're used to rules, algebraic rules with real numbers. But we do have to be careful about to discuss what we're to be careful about what objects you're talking about, whether you're talking about a matrix or a real number, a scalar, because some things will work with the scalars, but they won't work with the matrices. So you do have to be careful. So here's some basic properties of matrix addition and multiplication. So with matrices, A plus B equals B plus A. If you take any matrix, I'll just call this A1, A2, A3, A4. You can start to convince yourself that this is the case. B1, B2, B3, B4. This doesn't have to be, these don't even have to be square. They can be any size. As they do have to be the same size to add together. I'm just doing a 2 by 2 for simplicity. If I add these together, where this is A and this is B, my first element right here is going to be this element plus this element. So A1 plus B1. And the next element in this position will be A2 plus B2. So if we switch A and B around and do B plus A, oops, I did those multiplied. Those are supposed to be adding. So yeah, this is big difference. A plus B is the same as B plus A, but A times B, we'll talk about this later, but I'll emphasize it now. A times B is not always the same, okay? Sometimes they will be, but in general, A times B is not the same as B times A with matrices. Okay, so don't get that mixed up. If you switch B times A, then you're still going to be adding the same entries. I'll just be adding B1 plus A1. B1, A1, and add them together. And since the addition of real numbers is commutative, then these will be the same. A1 plus B1 is the same as B1 plus A1. So you end up with the same thing that way. Similarly, because real numbers are commutative, once you get into each of the entries, all of the entries that you're talking about, A plus B plus C is the same as A plus quantity B plus C. You can write out matrices A, B, and C just like we did here, and when you start adding up, you can just rearrange the order of the sum of each entry and realize that that's going to be the same. This is the zero matrix in number 3. So A plus 0 equals A. That's because if we have a matrix, any matrix here, and we add the 0 matrix to it, just each entry isn't going to change because you're just adding a 0 to that entry, so you still get the same 0. You still get the same entry. Here R is a scalar. R times A and R times A plus B is the same as multiplying R times A and multiplying this as R times B and then adding them together. That works in a similar fashion, or you can convince yourself in a similar fashion by taking R, you can write down a matrix 1, 2, 3, 4, plus 7, 8, 9, 10. These are any matrices. Again, as long as they're the same size, you can add them together. And If you multiply this out, well, you're not sure if you can multiply them out, but if we can add these first. So we get a 1 plus a 7, 2 plus an 8, 3 plus a 9, 4 plus a 10. We get all of that times r. And then a scalar times a matrix, as we learned last time. This r gets applied to each of the entries, so that is r times 1 plus 7, r times 2 plus 8, r times 3 plus 9, r times 4 plus 10. And then, since these are real numbers, we know that you can distribute, that multiplication distributes over addition. And so you can rewrite that as r1 plus r7, r3 plus r9, r2 plus r8, r4 plus r10. And now we can rewrite this as the sum of two matrices, which is r1, r2, r3, r4 plus r7, r8, r9, r10, and then we could factor out an r of from each of those, and so you get r 1, 2, 3, 4 plus r 7, 8, 9, 10. So you can see that if we keep the numbers separated, here I'm almost using the numbers just as variables, then you can once we get to a point where we know that we can distribute the r into the matrix, then you can do all of the real number algebra and pull it back out, and you see that multiplying r times each of those matrices first and then adding them is the same as adding the matrices first and then multiplying by r. So these kind of give you an idea of how the proofs work. The mathematician would just start with things like r times a1, 1, a1, 2, dot, 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 a1, n, a2, 1, and they would have lots of dot, 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 dots, down to a, m, n, stuff like that. Then they'd have a b, 1, 1. So they do with that instead of just to cover all cases instead of just a 2x2 matrix. All right, let's get back to here. And here you can, if you have a scalar times a matrix and you're multiplying that thing times the scalar, you can multiply the two scalars together first. I won't go through the proof like I did with the last one. So these are the kind of problems that we're not having you do this semester. So you can generalize the idea of independence and dependence to matrices. So if you can take combinations of one matrix and to make another matrix, then in the set, then they're dependent. But we're not going to have you guys do problems like this. Okay, properties of matrix multiplication. This is where you have to be a little bit more careful. Some things work like you would expect them to work, and others don't. We have a whole warning list coming up. See? Warning, warning, warning. Keep you from overgeneralizing. So the associative law of multiplication, if you're multiplying three matrices in a row, then it doesn't matter which order you multiply them in. You can distribute matrix multiplication over matrix addition, but you have to be careful because you have to be careful how you write these. After you distribute them in, you can't say A over B plus C. Once you distribute it in, you can't say BA plus AC or BA plus A plus CA. Okay, these are not the same. You have to, if A is on the left, when you distribute it in, it needs to be on the left of what's inside when you multiply. It's because, as I mentioned earlier, matrix multiplication doesn't commute in general. So, and that's why here we can distribute in from the right as well, except we need to keep the products in that same way. It's B times A, C times A. You can move your scalars around. So if you have R times a product, you can multiply R times your first matrix or R times the second matrix. R's are pretty flexible. And I, here where I is the identity matrix, or the generalized identity matrix, I times A is equals A. Like you can multiply both sides by the identity matrix. If it's square, the identity matrix looks like this, except it might be larger. You might have more ones down the diagonal. Okay, but here when it says it's an M by N, so the identity matrix of